Hello everyone, welcome to this new session on electromagnetic fields and transmission lines. Myself Dr. Sohail Rana, and today we will continue our previous discussion on magnetostatics. So today we will see few cases of BIOT-Savarts law and we will also see the Ampere circuital law. Before moving ahead, let us see the recap what we have discussed earlier. We have discussed about the properties of magnets and the magnet properties, then the relation of say magnetic flux density, that is B is directly proportional to the phi and inversely proportional to A. Then we have seen the direction of field of magnetic lines, so that is given by the right hand thumb rule. Then we have discussed the relation between B and H, that is very important. It is given by B is equal to mu H. Then we discussed BIOT-Savarts law. In BIOT-Savarts law, we have seen that H magnetic field vector is given by IdL cross AR cap divided by 4 pi R square. So this equation is important for our next topics. Then we have seen the cases of magnetic field intensity. First case we have seen about the infinite line charge and we derived it and we got the derivation as H bar equal to I R divided by 2 pi R into direction. Now we will see the case of finite length conductor. Now in previous session our setup was related to infinite line. Now what we have to consider? We have to consider a finite line. How will be the behavior of finite line? So what we are doing, basically we are just studying the effect of magnetic field H or B in the surrounding region. So here we are considering one test point or test charge. So this is our test charge. This test charge is present on the floor. Floor, the place, this plane. On this plane, the values of Z are 0. Now as we are considering a cylinder, and that cylinder we are imagining that it is present on Z axis. On Z axis we have placed a finite length conductor with length L, right, and out of that we will consider small differential length dl. As it is placed on Z axis, dl we can call as dz. Now this is like a source, like an antenna. He is spreading his lines across, so we will call it as a source, and these source points we will have 0, phi and z. So its effect on point charge we have to study. So say that vector we will call as R bar. Now let us consider the various angles. So the bottom limit of the conductor making some angle, say theta1 with the point charge. Say R bar is making some angle theta, and the upper limit of the conductor is making say theta 2. So this is our setup. Now what we have to do, we have to find out the magnetic field intensity equation for this setup. So already we have, say, dH from BIOT-Savarts law. We have basically what we have, say, I dl sine theta, say, AR cap, the direction in towards radius constant, by, say, 4 pi r square. Now here we can do some substitutions. So what substitutions we have to make here? Say we will have say in place of IDL, in place of, now IDL is present on z axis, so we can keep it as IDZ. And in our previous example we have derived the expression, that basic expression will be same. Say it will be dH bar equal to I dz by 4 pi into r square plus z square to the power 3 by 2. Now this is our expression. Up to this it will be common with infinite line. So now what we have to do, we have to consider the limits. Now the conductor is present on z axis, so it will have some limits, length 1, length 2. Suppose this is a coordinate system. Here we are taking small conductor, say from L1 to L2. So as it is on z axis, so we can take it as Z1 to Z2. So if we integrate, we can find out H for the entire region. So say we will get H bar equal to, the limits will be from Z1 to Z2, say I d Z R A phi cap divided by, we have 4 pi into r square plus z square to the power 3 by 2. Now let us take out the constants. So the constants, we have ID, this I current is constant here, so we'll take out I by 4 pi and this A phi cap. Inside we'll keep only dz term, which we have to integrate, so it will be dz r divided by r square plus z square to the power 3 by 2. Now this one is a complex term, so what we have to do, we have to substitute, we have to consider substitution to simplify this term. So we will focus on this one and we will use some substitution there. So let say tan theta is equal to z by r. So then what we can say, z is equal to r tan theta. So dz will be equal to r secant square theta d theta, right? Now by substituting this in place of r, we can keep so this is r equal to z tan theta, we can keep. So here we will replace these terms. So what will be the change here? So if we put this, for this we can write it as, say, r square plus r square tan square theta to the power 3 by 2, and we'll get it by simplifying. Say we'll get r cube secant cube theta. So we can simply replace this value there. So let us replace it. So limits will also change. Now for limits, so new limits will be, so previously we had z1, z2. So when we have z1, then theta will be theta 1, and for z2 theta will be theta 2. Now let us put the new values. So what we will get? We will get, say, h bar is equal to I by 4 pi a phi cap, the limits from theta 1 to theta 2. So these are the limits. So say r secant square theta d theta divided by r cube secant square theta, right? So further we can simplify it. Say h bar is equal to I by 4 pi r square theta 1 to theta 2. Now these terms we can cancel, so this we can further simplify as, say, cos theta d theta divided by r square. So now further if we take integration, so what we will get? H bar equal to I by 4 pi r square a phi cap sin theta for limits from theta 1 to theta 2, right? So we'll put the limit, so it will become sin theta 2 minus sin theta 1. So final will get, say, h bar is equal to we'll get, say, h bar equal to I by 4 pi r sin theta 2 minus sin theta 1. Now what we can say here, now this is general expression where point is on the floor. Now we can have different location of the point. For example, in our derivation we considered the test point is available on the floor, that is z equal to 0 plane. Now what if our point is placed like this? If point P is placed like this, which is hanging, say, in the space, so this is our, say, this is our test point. So this is the test point. So this is our test point. So there may be different points at different position. Some may be at the center, some down, some above. First we considered test point was here. Now we'll consider here. Now, so this is the theta 2 and this is the theta 1. So for this case we can get some situation where the point P is present at the center of the conductor. So this is point test point here, right, and this is at the center of the conductor. So according to that, the limits for theta 1 and theta 2 we have to put, and accordingly we will get the answer. Okay, now let us discuss third case. Now in third case we have one sheet, square sheet, and that sheet is filled with flowing current, and that current is creating magnetic field around it, right. So this is our setup here. Now in this setup we will consider one square sheet which is present on the z equal to 0 plane, right, and this complete sheet is applying some magnetic field intensity. Say this is our test point at the center of the sheet, and say this is 45 degree, this is 45 degree, and the both points are say r phi 0, this is r by 2, and current is flowing in all the branches, and due to that there is magnetic field. So from four sides we have to consider. So we can say we have H1, H2, H3 and H4 for these all different currents. So suppose if current is moving like this, the magnetic field lines will come outward. So in similar way all the different current carrying conductors will have a different direction for magnetic field. So let us check it how we will get it. Say we will consider our last expression. So total H will be equal to total H will be equal to addition of H1, H2, H3 and H4. So already we had derived one expression. So that expression, now say they have some distances A, B, right? It is square, so all distances, all sides will be same. Say AB will be equal to say BC equal to CD. Let us consider it as say R. Okay, so and the half distances between them, say we have PM or CM will be equal to R by 2. So we should draw the diagram and refer our discussion with the diagram. Now we have two angles with test points, say theta 1 is minus 45 and theta 2 is plus 45. So let us keep it in our expression. What is our expression? Say H bar equal to I upon 4 pi r sin theta 2 minus sin theta 1. So theta 1, theta 2 we can keep plus minus 45. So after keeping this we will get say H bar will be equal to, say first we will calculate H1. For H1 we will keep the values for one side 45. So we will have say I upon 4 pi. Now R is half distance there. So say that is R by 2. Then here we will have say plus sine 45, this minus will become plus. Again we will get sine 45. Okay, so that sine 45, if we calculate, say we will get, if we give the value of sine 45, we get now h1 is equal to I upon 4 pi r by 2, then 1 upon root 2 plus 1 upon root 2. Okay, so now we will simplify this term. So after simplification, we can rewrite it as, say, h1 equal to I root 2 divided by 2 root 2 pi r by 2. So this will be the, further we can simplify it, say we can write it as h1 equal to I upon 2 root 2 pi r by 2. Now further we can simplify it, say we can write finally some h we will get, say h1 bar will be equal to I upon root 2 pi r. Now all the sides have same distance, same current, so all of them will apply same amount of magnetic field intensity. So what we can say, h1 is equal to h2 is equal to h3 is equal to h4, because on this square all of them are applying, say h1, h2, h3, h4, they are applying same amount of magnetic field intensity. So these are all equal. So already we have h1, so we have all the values. So total h will be equal to addition of all these 4, so we'll get 4 times I upon root 2 pi r, or we can simplify it as, say, h equal to 2 into root 2 I by 4r. So magnetic field intensity is acting on z axis, so we can add z axis direction component to make it vector. So this is about this one. Now let us consider the next case. Here we will take the example of circular ring or circular filament, and that circular ring is applying magnetic field intensity in the surrounding region. So it is applying magnetic field intensity in all the regions, but we will consider one test point. So here we will consider our test point. So this test point is the place where it is applying the force. So now we will stop here with this discussion, and this case along with next topic we will continue in the next session. Thank you. Have a good day.